the folder. Oh, it's not actually shown here, is it? That's annoying. So let's go back and start from scratch. So in the SAR training area, notebooks, SAR training, English UNAVCO InSAR. Under here is ICE2 docs. Under ICE2 docs is notebooks. Now let's take a little detour first just to clue you in. Under last year's notebooks, there is a theory notebook section that has a PowerPoint, which includes all the SAR and InSAR and correlation notes as PowerPoint. Those notes were converted into a notebook, but in a very rudimentary fashion. It was simply taking screenshots, basically making images of the PowerPoint slides and putting them into a notebook. So it's really no different, except for a few equations that were added in various places. It's really very little different from the PowerPoint itself. This year, I made the effort so now we're in UNAVCO 2020, that's this year, going into theory. You'll see that there are now 3 subfolders. The SAR subfolder has a SAR notebook, which is very much the same as last year's. In fact, I don't think I've changed it at all. I didn't have enough time to recast this one. So hopefully in the pre-course time period, you clicked on this, ran all the cells, and were able to at least follow through this a little bit. We also had a recording from last year that hopefully you could follow through as well. So we're not going to cover this today. I will be referring to some of the content here, so I hope you have some familiarity. In some ways, you could argue that what Gareth told you earlier about InSAR displacement is really the fundamentals of what you need to know. So most of what I'm going to say is sort of details and further insight. So we'll start with the InSAR notebook, UNAVCO 2020 Theory InSAR. And after this, we'll go to the correlation notebook. Okay. That's just background. So here we are. That's the SAR. Hold on a second. Here we go. So here we are in the SAR interferometry notebook. And this deals mostly with the geometric aspects of InSAR, much of which should be familiar to you from what Gareth was saying. So I worked on this with Scott Hensley. I don't think he's on the phone now, but he and I have developed these notes over the years. So starting out, we're going to talk about the relationship of phase of a radar wave and the propagation distance, which is effectively what Gareth was telling you about earlier, concept of interference, and how you can use this interference of phase to either measure topography or surface displacement, and what the different sensitivities are between measuring topography using this interferometric technique and surface displacement. So it's a very limited scope here, and hopefully it is simple enough to follow in a short amount of time. So if you read the SAR notebook, you'll know that electromagnetic waves can be represented by propagating sinusoidal waves where their amplitude is changing in a sinusoidal fashion. Complex waves can be combinations of sinusoids, but at their fundamental form for radar, we think of it as just radar transmitting a wave that is a sinusoid scattering off of an object and propagating back to the radar as a sinusoid with perturbed phase. So the phase of that wave is characterized by the expression 2 pi times the range distance, which is rho here, divided by the wavelength. So the phase is a encoding effectively of the range. Rho over lambda is the number of wavelengths. Multiply that by 2 pi radians, and we get, which is radians per wavelength, and we get the phase of the measurement. So if all were perfect and we could measure the absolute phase, then we could get an absolute range measurement. And depending on how accurately we could measure the phase, we could get that level of precision or accuracy in the range measurement. But typically, these wavelengths, as we talked about, are in the 3 to 80 centimeter range for a typical radar. And if you can measure down to a fraction of that wavelength, then you're measuring the relative range down to millimeter kind of accuracy. So for interferometry, we can't really measure the absolute range, but we make difference measurements between two or more different observations. So it's those difference measurements that we are sensitive to. So the concept of interference is pretty straightforward. It's illustrated by this lovely graphic off of Encyclopedia Britannica, better than anything I could draw, where we have a wave source illuminating a couple of holes in a plate, and that then gives you a nice coherent source of oscillation of waves propagating through that slit with the same phase at this particular point. They propagate out, radiating like water waves, and at a particular distance, the waves will intersect a plate, and depending on the distance from the slit to that point on the surface, you will get either destructive interference, as you see here, or constructive interference, as you see down here. And as you move along the plate, you'll get alternating constructive and destructive interference. So this is a representation of the intensity of the light that you would see on this plate if it were a photographic plate. And even though the wave is oscillating quickly in time, you would get this kind of a fringe pattern. If we could somehow measure the phase on this plate, we had a phase detector, the phase would be constant at each of these points over time, but it would be changing proportional to the relative distance between the two. We can only really measure phase between minus pi and pi because of the way we capture it as a complex number. And so we would see on our phase detector minus pi to pi. Hold on, let me make sure everybody is muted. Looks like most people are. Okay. So in SAR, in synthetic aperture radar interferometry, we have our synthetic aperture radar in space, and for this discussion, we'll focus on the case where we have two separate radars in space looking at the surface from slightly different vantage points separated by a distance b. The wave propagates down, radiates with its constant phase surface as shown, and interacts with the surface. The other observation from a slightly different vantage point demonstrates an interference pattern with the original wave, just as you saw in the figure above here. So as you look on this surface, which is like our photographic plate up above, we'll see phase differences, which are related to the relative, the intersection point of these two SAR signals. Of course, the signal propagates back to the radar as received. We create a so-called interferogram from that, which then encodes the phase. So if we call S1 our first image, and S2 our second image, that's the image acquired by point 1 here, SAR1 and SAR2. And these are, of course, a function of position, the range, and the along track position. X is the along track position as the SAR flies into the computer screen here. If we can form an interferogram by taking the first image, and for each point, take the complex conjugate of the second image and multiply the two. This then gives you an amplitude product and a phase difference product because of the complex conjugate here. So this shows you, since the phase is proportional to range, this phase difference then would be proportional to the range difference. Okay, so for a standard SAR image, if you had looked at the SAR notebook before, you would have seen some examples of the radar backscatter as a function of position is related to the intrinsic roughness of the surface at the wavelength that you're observing, and also to the topography. The topography modulates the brightness because of the area that is presented to the radar. So you can see the effects of topography in this image very clearly, but you don't actually get a topographic measurement. However, if you look at the phase of that topographic measurement through the interferogram, then you can see that the phase difference, that is phi1 minus phi2, looks very much like a topographic signal. So because the range difference is changing as a function of topography, the interferogram is coding the topography. So here is the equation for describing that. It's very simple to first order, more complicated in practice, but for our purposes, we'll just say that the phase difference, delta phi, is proportional to this range difference, which is this number here. So image 1 has range rho, image 2 has range rho plus delta rho. So once we've measured delta phi through the interferogram, we can invert this for what our range change is. This value p we'll talk about on the next slide. It's either 1 or 2. So having measured that, we can solve for delta rho, and with delta rho, we can use the law of sines to triangulate to calculate the height. So if we know the baseline, which we typically do for our interferometer, we know the range, at least a sufficient level of accuracy, and we know the angle of the baseline, which is this angle here, we can use that information to calculate with the estimate of rho, delta rho, from delta phi. We can use that to calculate theta, which is the angle between the vertical and the direction we're pointing. So through this, we can reconstruct the height. That should be a minus, not an equal sign there. I can fix that. There we go. Okay, so that's all there is to topographic mapping, at least the first order. We can estimate the height based on the interferometric phase once we know, if we know the geometry of the interferometer. So let's define P here. There are different ways of acquiring data. And one is the case where you transmit off of one antenna and you receive at that antenna. You also receive the echo at a different antenna, and then you make the interferogram from these two separate observations. Okay, that's what we call the classic mode, and P is equal to 1 in this case. If you go through this math, it's quite straightforward. The other mode is called dual antenna mode, or otherwise ping pong, where you transmit off of one antenna and receive of the same, and do the same off the other. Typically, this would be done with an alternating kind of measurement scheme. If you go through that geometric or mathematical calculation, it's clear that P in this case is 2. So these are the two different collection modes. For the purpose of our class, I should run all these cells. Sorry about that. Back. So for the purpose of our class, we are mostly focused on repeat pass interferometry. And I'm going to let you do this exercise to figure out whether P is 1 or 2 for a repeat pass interferometer. Okay, so let's relate the interferometric phase to the interferometric baseline. We usually have several slides on this topic, but I've distilled it down to a very simple set of equations here. So this delta phase, once you go through the math, is basically 2 pi p over lambda times the look vector that Franz and Gareth talked about, projected on the baseline vector, or vice versa. The baseline vector projected onto the look vector, which is a better way of characterizing it. So here's the baseline vector separating our two observations. We project it onto the look vector, and this is what the phase that we're measuring, the first order, is. And if you were to just assume that you're in 2 dimensions here and you characterize B according to this 2-dimensional vector, B cosine alpha, B sine alpha, and the look vector in this geometry is sine theta minus cosine theta, where theta again is measured from the vertical to the look vector, then you get this sort of classic formula for the phase, the differential phase, which is that it is B sine theta minus alpha. So again, if you have this delta phi measurement, you can invert this for theta by taking the sine inverse, and then you can solve for the topography that way. Okay, so you'll see this formula often, and it's going to be used as we go down here as well. Something that's of interest is the phase gradient. In many of the things that we study, phase gradient tells you the change in phase is a function of range or the along track position. And when you look at an interferogram, that phase gradient may be apparent to you depending on what the baseline actually is and how the data are processed. So again, here's the formula from the previous cell. If you just take the derivative of that with respect to range and the along track position, this should say actually X, not S, because I've switched notation, but in any case, that gives you this. The derivatives are basically B is fixed, the baseline is fixed, so this just is the projection of the baseline on the derivative of these vectors, of these line of sight vectors. So if you go through and do the calculation, you'll see that the change in phase, change in the differential phase as a function of the change in range is given by this formula here. It's proportional to the perpendicular component of the baseline. So B sine theta minus alpha was the parallel component. Perpendicular component is B cosine theta minus alpha. So that would be up here, this component, this dotted line. Okay, so B, it's proportional to that, and it's inversely proportional to the range. So as the baseline becomes 0, this change in fringes across the surface becomes 0. Okay, so that makes kind of sense. You don't have any sensitivity really to the topography if you have no baseline for this particular observation. And then here's the formula for the fringe rate in the along track dimension, also proportional to that. Yeah, the psi, these are the local slopes. Do I not define that here? Yeah, I need to define those. Those are the slopes which modulate the fringe rate when the topography is tilted up or down. So yeah, I will fix that in the notes. Thank you very much for that comment. I'm sorry if I'm missing a lot of comments as they're coming along. I just see what pops up at the top of my screen. In any case, even if you have no topographic relief, you're going to have, with a baseline that's non-zero, you're going to have some change in the phase going across the surface, even with a flat surface. So one thing we typically do to make it look like a topo relief map is we remove that flat, the fringes that are just due to the flat Earth. And that's done by looking at calculating what the fringes might look like relative to a reference surface, which this L0 vector here points from the position of the interferometer down to a point on this reference surface down here. The actual observation is up here someplace. So by going through this calculation, this is the actual phase. We subtract off a version of that phase, which is relative to a reference surface. We're left with just the variability above that reference surface. And again, in the interest of time, I won't go through the equations here, but by going all the way through this, you'll see that the flattened phase, after removing that, then is proportional to the perpendicular component of the baseline and to the topographic height, ht. So this says then if the perpendicular component of the baseline is 0, you have no sensitivity to the topography because your measured phase will be 0 in that case, independent of what the height actually is. It also says that this flattened phase to this approximation is directly proportional to the topography. So if you measure this flattened phase, you measure the topography with some scale factor. These are all approximations, and the details if you're actually doing topographic mapping, need to be explored in the literature. There's lots of literature on this topic. But this gives you the heuristic feeling for what the phase actually means. There's some convenient term called the ambiguity height, which characterizes the variability of phase with height. I'll let you do that as an exercise. And we will move on now to what is most relevant for this class, which is differential interferometry or repeat pass interferometry. So in this case, we are hoping that the baseline is 0 because we're not interested in topography. We're interested in the change that Gareth was talking about at the very beginning of this course. So in that case, we're hoping that we're going to fly back to exactly the same point from one time to the next, and that the ground will have moved by some distance, and that the range that we measure, that range change due to the phase difference, will be measurable, and that we can then estimate that range change. So in this case, now we have delta phi is 4 pi over lambda times the range change. That's what we had before. And if you haven't taken the quiz above, I think you know what the answer to what p is for this particular case. And so now this is directly proportional to the range change itself because we have no baseline. There's no sensitivity to topography. In this case, we define the range change as the projection of our displacement vector onto the look vector. This notation is different from Gareth's, but it's the same basic formulas. All right, so that's simple enough. Typically, we have a baseline that's associated with this measurement because we can't fly our spacecraft to exactly the same point in space over time reliably to the accuracy that we would like it to be 0. So we actually, in our measured delta phase, we have 2 terms. We have the topographic term, which we saw before, and we have the displacement term. So we can still flatten this interferogram, and in that case, the flattened interferogram then has our range change term, and it has our topographic term. And if we want to only study the range change, we have to remove this topographic term. One way to do that is with a known digital elevation model. You can then substitute in values for each range and position, azimuth position. You can substitute in here the height, calculate what this is, and subtract it off from the interferogram, and you're left with just the change. Okay, so interferometric sensitivities. So we usually say that differential interferometry detects millimeter level surface deformation because you are measuring the range directly with 0 baseline. It's much more sensitive to displacements than it is to topography. And you can see that through these equations. If you calculate for the topographic case where you have a baseline of some length, if you calculate the change in the phase with respect to height, you get this expression related to the ambiguity height that's up above, which has this b cosine theta minus alpha term in it. You see it has b and rho in the denominator. So this number, b over rho, is very, very small typically. The baselines are on the order of, let's say, 100 meters or even 1,000 meters, and the range is usually on the order of, say, 1,000,000 meters. So this number, this ratio is very small, so the sensitivity, that derivative, is quite small. Whereas in the case of the displacement, if we take the derivative of the phase with respect to the range, it's directly proportional to this constant. So and this number is much larger than something that's 1 over 1,000. So typically we are much more sensitive to displacement because it's a direct range measurement as opposed to the topographic measurement, which is a triangulation measurement. Okay, so there's a little exercise here. I did have time to put in one calculation, which basically implements these formulas for you, and you can calculate d delta phi d height and d delta phi d rho, and get the numbers here. Sorry, I didn't round them properly for you. And you can use that to answer this question on sensitivity. All right, one more thing on phase unwrapping. This is usually a larger section, but we don't have a whole lot of time today, so I've summarized it in one slide. So again, here is our interferometric phase difference. It's the topography term and the displacement term, both projected in a line of sight. What we measure is the interferogram, and the interferogram is a complex quantity. So what we get to get the phase, we take the inverse tangent of the imaginary over the real part of that complex number, point by point. And so what we really do is we measure the phase that we want modulo 2 pi. So this is the case for topography, and you can see that we have a baseline. This is the phase of the b dot L, and it's obviously not the actual phase is not modulo 2 pi, the phi topo, but when we calculate it, we just get phi modulo 2 pi. So there is a process of unwrapping, which Franz mentioned earlier, wrapped and unwrapped, where we take the measured phase and we figure out what the actual phase was to within a constant. So here's a simple example, simple one-dimensional case with no noise, where our actual phase looked like this. This is what we actually measure, the wrapped phase, modulo 2 pi, minus pi to pi. And in this case, we started our unwrapping process here in the middle, and we worked our way outward, and we looked for phase jumps, and we just adjusted the phase by 2 pi until it looked fairly continuous, and we got this nice curve here. You can see, of course, it looks very similar to the actual phase, but we're off by a constant. So in the real world, phase unwrapping is much more challenging than this simple problem. It's in 2 dimensions. There's noise, there's shear, there's all kinds of factors in the data that cause unwrapping to be a challenge. But in principle, this is what we're doing. We're just taking the measured phase modulo 2 pi, unwrapping it, and we get the right answer to within a constant. All right, there's a number of interferometric error sources. We're going to talk more about the atmosphere and the ionosphere on Wednesday, I believe, and I mentioned that up front. You can have phase unwrapping errors due to the complexity of that problem. We can have interferometric decorrelation, which I will talk about more in the next module. There's a number of other more system-oriented factors like layover and shadow, which you hopefully read about in the SAR tutorial, scattering properties, ambiguities, things like that, which are difficult to really understand, so we don't really cover them here. Just a word about the tropospheric noise, which is one of our dominant error sources. Because we're flying repeat paths, we fly over once, we fly over again another time, and the troposphere down here, which causes a delay in the phase because we're not propagating through a vacuum. The troposphere changes from time to time and therefore introduces a variable signal. And if you were to plot what that troposphere might look like according to theoretical models, your interferogram with zero deformation but with troposphere might look something like this. So it's a significant source of noise in our measurement. And the biggest challenge is that if you look at the way it is introduced into our phase measurement, it is effectively indistinguishable from the displacement that we're interested in. It just sums to it. So because they're indistinguishable and it's a significant magnitude, it's an issue. And you'll see throughout the course the time series analysis how to address this. All right, there's one simple homework to drive home the ambiguity height and the fringe rate issue, so I hope that you'll take care of that. You can either do it in the notebook directly, just create a cell and do the calculation there, or you can submit it separately as a PDF. It's up to you. So that's it on that. I'm not quite done yet. I want to go over the correlation. I've taken half an hour, so I'm not too far behind. While I'm getting the other notebook up, if there's any quick questions, I can't really easily look at the chat window, so if somebody else can interpret it while I'm bringing up the other notebook, that would be helpful.